All right, let's get started. Today, we are going to continue our discussion from last time on radiation, at least the heat transfer by radiation. And so what we discussed in the previous lecture, first of all, was the conceptual view of how light or energy is radiated from an object. And what we said was it basically has to do with the different energy states of electrons in their orbits around the atom. As you excite these electrons, they get to higher energy levels. Eventually, though, they want to go back down to their lower energy levels, and in doing so must give off that excess energy. And it does it through the use of light. It sends off photons or light, which is energy. And the energy, or the light, depending on its energy, will be different frequencies. And when we say different frequencies of light, the one way of thinking about it is you can think of it as different colors. Of course, truly speaking, the colors are in the visible spectrum, but there's more colors than our eyes can see. There's an infinite amount of colors from the lowest energy, the lowest frequencies, up to infinite frequencies. And there's a certain range of frequencies, a certain range of energies, which we call heat. And that's usually in the infrared spectrum. And so we have a conceptual view of what's going on with the electrons in an atom, giving away this energy. And it all has to do with the temperature of the object. The hotter you get an object, the more excess energy it has to apply to the electrons to get them to higher and higher excited states. And eventually you get things hot enough where the energy that the electrons release when they drop back down is high enough energy to be in the visible spectrum. And so we see glowing embers, or we see the heating element on an electric stove turn bright orange and red as it heats up. But we went further. We also talked analytically about what kind of problems we can try to calculate answers for as it pertains to radiation. And what we found was the big equation was Q over T, which you can either think of as the heat transfer rate, like we did with conduction, or another way of thinking about it, another name we could call this quantity, is that the power radiated is given by sigma epsilon A T to the fourth power, where sigma is the Stefan Boltzmann constant, and that is 5.67 times 10 to the minus 8. Epsilon is a number which deals with the material. How good does this material radiate? Is it a perfect radiator? Then it's an epsilon of 1. If it's a poor radiator, then it's near 0. And the problem will generally say this object radiates at 35%. And so you'd say the epsilon then must be 0.35. A, capital A, is the surface area of the object. And this obviously comes because as energy, as light is trying to leave the object, radiate away, only only those atoms or those electrons which are on the outer surface of the object will allow the light to escape, because any of the atoms on the interior of the object, when it releases the light, which it will, that light is quickly absorbed by another atom in the object. And so the light just gets moved from one atom to the other as it travels its way to the outside until eventually it gets to the outer surface, at which point when it leaves the outer surface, that's when it's able to leave and go off to infinity. And so the bigger the surface, the more surface you have, the more places energy can be radiated away. And thus, we have a dependence on the surface area of the object. And then finally, the temperature And in fact, in this case, radiation is fairly unique in that its equation tells us the power is proportional to the temperature to the fourth power. So a change in the temperature makes a huge difference to the amount of energy that'll be released because you raise that temperature to the fourth power. And again, because this particular equation just has temperature in it, not delta T, not the change in temperature, we have to convert our units for temperature to Kelvin. We're not allowed to use degrees Celsius here. And so that's what we discussed last time. And so, for example, a quick problem, which we may use this equation for, is something like a star has a radius of 5 times 10 to the 8th meters. It acts as a perfect radiator with its temperature being 10,000 Kelvin. Calculate the power radiated by this star. So there's an example, a nice basic problem which deals with the radiation. So what I want to do, of course, I've only got one equation to use for radiation, and that is Q over T. The power radiated is sigma epsilon A T to the fourth. So I want to plug my numbers in. What do I know? Sigma, that's just a constant, so 5.67 times 10 to the minus 8. Epsilon. Epsilon is how good does this thing radiate? Well, I'm told in the problem it's a perfect radiator. And when I see that, what I'm told is epsilon is equal to 1. That's what it means. What about the surface area? Well, I know area, surface area of a sphere, and a star is a sphere, of course, is 4 pi r squared. So I have 4 times pi times the radius of this star, which I'm told is 5 times 10 to the 8th meters squared. And then, of course, the temperature to the fourth power. I have the temperature in Kelvin, so I don't have to convert it. I just stick it in to my equation. And there we go. There's my equation with all the numbers plugged in. At this point, it's just a matter of using my calculator to try to get an answer. So I start. When I look at this equation, remember, I don't plug everything into my calculator all at once because I usually make mistakes when I try to do that. Instead, I try to do one little calculation at a time. So when I plug it in a calculator, what I'm doing, I see the most complicated part is the part with the radius squared. So I do 5 times 10 to the 8th and I get a number. And then I square that number. Then I multiply it by 4 and then by pi. And then I multiply it by 10,000 raised to the fourth power. And then I multiply that by 5.67 raised to the minus 8 power. And I get 1.78 times 10 to the 27th watts. All right. So that's how we use the equation. We're given a bunch of data about the object. I just plug the numbers in, making sure all my units are correct. I need meters for the radius, Kelvin for the temperature, and so on. Now I could always ask a part B as well. I could say, okay, given I know the power, I want to know how much energy will be radiated after 1 day. So I'll do a part B. How much energy will this star radiate in 1 day? Well, all I have to do, I know the power. Power is Q over T. And I know that number now is 1.78 times 10 to the 27. But what I want is just the Q. I want how much energy, knowing that the time is 1 day. So the first thing I'm going to do is I'm going to say, how many seconds are there in 1 day? So T will be 1 day. And I know that in 1 day, there's 24 hours. And I know that in 1 hour, there's 3,600 seconds. And so if I do this little calculation, I'll have my final answer in seconds. So I say 1 times 24 times 3,600. And I get that in 1 day, there's 86,400 seconds. So now I know the time. Remember, a lot of physics is all about using the correct units. I may have the right equation, but if I'm using bad units, I'll get a wrong answer. I'm told I want how much energy will it radiate in 1 day, but day is a bad unit of time. What I want is seconds. So I have to convert 1 day to seconds. And this is how I converted it. I now know the time in seconds, so I go back to my original equation, solve it for Q. I have Q is 1.78 times 10 to the 27 times T, and T is 86,400. And so now I get my final answer. The total amount of energy radiated by this star in one single day is 86,400 times 1.27 raised, 1.78 raised to the 27th power. 1.54 times 10 to the 32 joules. Heck of a lot of energy. Of course, it's a star, so you would expect a star to radiate a lot of energy. It's a big nuclear furnace, constantly exploding forever. Well, not forever, but for billions of years. And every day, this much energy comes out of the star. So any questions about this example? This is a nice typical example of radiation. You have an object, you're given some data about the object, how hot is it, how big is it, things like this, what's its shape. And we do a basic calculation to figure out the power of the object. And from there, we can then do other things. We could say, if I want to collect 20 million joules of energy, how long should I wait? Well, there, you're looking for a time, how long should you wait, given that you want this number of joules, this Q. Or anything, I could say, how big should the star be for this to be true, and so on and so forth. At the end of the day, you have this one equation, you're given a bunch of information in your problem. The key is make sure everything is under the correct units. Once you have the units, you plug all the data into the equation and you get your answer.
And if we were like given the time already and want to find, not at the time, if we're given the like the amount of energy it releases, and you want to find the time, you divide by Q, right?
What you would do, right? Let's look. Let's see exactly what we'd have to do. So pretend we already calculated this number, the power. We did that already. Now part B says, how long should you wait for such and such and such? That means I want T. Well, if this is my equation, And what I want to find is T. I need to manipulate the algebra to get T by itself. Well, if I try to divide by Q, notice what would happen. If I divide by Q, the Q goes away on the left, and I'm still left with 1 over T on the right, and now I have A over Q, 1 over T on the left. Now I have A over Q on the right. But this is bad. I don't want 1 over T. What I want is T. So I don't want to do it that way. Instead, what I'll do is I say, look, the T is on the denominator. I want to get it up to the numerator. I eventually need it in the numerator. So I'll first multiply by T, right? And that leaves Q over here by itself. And now I have A times T on the right. The next step is I don't want A times T. I just want T. So now I'll divide over the A. And now I have T is Q over A. So that's how I would do it. Given you want to find the time, it's just an algebra problem. Solve for the unknown. The unknown happens to be in the denominator. So the first thing I do is get it up to the numerator. Once it's up in the numerator, then get it by itself by moving everything else to the other side. And in this case, it happens to be T would be Q over A. Okay, so does that make sense?
Yeah.
All right, cool. Any other questions about this type of example? All right. Yeah, there's not too much involved here. It's pretty straightforward in that you have one equation sitting there, and you basically have to plug all the numbers in, and there's one unknown sitting there. However, of course, we're going to now get a little bit more realistic in our problem, because what I actually did here was a special case. This is a special case, assuming that the object, which is going to radiate, is placed in a location where the temperature of the environment is 0. So maybe you're in outer space. Of course, truly speaking, in outer space, it's not 0 temperature, but to an approximation for us, we just pretend outer space is at 0 Kelvin. But of course, this isn't realistic. If we're on Earth and we have our charcoal lit up and it's burning embers right now and is glowing, that charcoal is not sitting in an environment at 0 temperature. It's in some temperature. Maybe it's whatever the outside temperature is. Maybe it's in a barbecue pit, and so the temperature of the pit itself is fairly hot. Well, if you recall from when we talked about things like conduction or calorimetry, if you have two objects that are far apart in temperature, then the really hot object really wants to send its excess energy to the cold object. Whereas if you have the two objects are really close in temperature, then there's no real pressing need for that extra energy to move over to the other side because they feel pretty much the same. And in fact, if they're exactly the same temperature, you don't move energy around. Well, the same thing is going to happen here. If you have a radiating object, but the surrounding temperature of that object is pretty close to the temperature of the object itself, then it's not going to radiate all that much. Whereas if you stick it in a very cold environment, it radiates a lot. So what we want to do is modify or generalize this equation to cover more examples. And the examples I want to cover are when we put this object in an environment with some known temperature. We already have the special case. If the known temperature of the environment is 0, well, we get what we just been doing, the normal radiation equation. That's all it is. However, if it's not 0, if we know the temperature of the surroundings, now we got to do something different. And so what we want to do is modify the equation. Everything else should stay the same, sigma, epsilon, A. But now what we have is this temperature thing that we have to worry about. And I know at the end of last class, I kind of foreshadowed what's going to happen. And so we've all been spoiled by the answer, but let's walk through it anyway. Usually what would go here is t to the fourth, but now I have two different temperatures. I've got the temperature of the object and I've got the temperature of the environment. Okay. And of course, this amount of radiation you get should depend, or how quickly it radiates, should depend on kind of the difference between these two temperatures. If there's a big difference, it should radiate really quickly. If there's a very small difference or no difference at all, then it shouldn't radiate at all, or at least very slowly. And so certainly what would go here instead of just t to the fourth should be something like a difference in temperature. But the problem is I have two ways of doing this. I could either call it delta t raised to the fourth power, which would be temperature of the object minus temperature of the environment raised to the fourth power, right? The difference in temperature, you get that number and then you raise it to the fourth power. That's one version. Or the other thing we can do is say the temperature of the object to the fourth power minus the temperature of the environment to the fourth power. Okay. So that's like a delta T, that's like a difference in temperature, but instead of it being the fourth power of the difference in temperature, you're finding the difference in the fourth powers of the temperatures. Okay, so when you take the fourth power is going to matter. These two things do not equal each other. Okay, and we can test it. Let's test it. Pretend temperature of the object is 2 and temperature in the environment is 4. Okay, so is this the same as this? That's what we want to test. If they're the same, then we don't care. We could just choose either one. If they're different, then we have to figure out which is right. Well, 2 minus 4, well, that's -2, and -2 raised to the fourth power is 2 times 2 is 4 times 2 is 8 times 2 is 16. So this would be negative or positive 16. The other answer, 2 to the fourth power is 16, minus 4 to the fourth power. Well, okay, let's see. Is 4 times 4 is 16, times 4 is 64, times 4 is 256. And so 16 minus 256 is minus 240. Aha, two different answers. So certainly, which way we take the fourth power will matter here. These are not the same things. Well, instead of trying to go through all the analytical and theoretical derivations, I'll just give you the punchline. Of course, what probably happened is people did a bunch of experiments, got results, and used the results to figure out which of these is the right way to do it. Sometimes that's how physics works. I'm a theoretical physicist, so I work a lot with the mathematics, and I do no experiments. Other people are experimentalists. They work a bunch of experiments, and they use the results of the experiments to try to figure out some law. Some people work the math to figure out the law. Some people use data to figure out the law. Well, if we use the data from experiments, we find out that this is the correct way to do it. It's the fourth power of the temperature minus the fourth power of the temperature. So our new equation, Q over T, the power radiated by an object, is sigma epsilon A times the temperature of the object to the fourth power minus the temperature of the environment to the fourth power. Now, it would be nice if it was the other way, because then it's just delta T to the fourth power. And if it's delta T, I could start using Celsius again, and I don't have to use Kelvin anymore. But obviously, we know the results. The result is, sorry, it's not delta T. You have to do the temperatures again. So you have to have Kelvin here. You can't use Celsius even with this modification. But so be it. This is it. This is the result. This is the main radiation equation. We get back to the old equation if we let the temperature of the environment be 0. Then this term would drop out, and all you'd have is the original equation. But this is the general one. This is the major one. All right, well, that's not too bad. That's not too hard to, it's not a big difference. So let's try an example. What does an example of this style of problem look like? Well, let's say you have a solid sphere of radius 30 centimeters, is heated to, let's say, 800 degrees Celsius. This is a very bad sentence, but don't worry about it. You place this sphere in a container whose temperature is, let's say, 30 degrees Celsius. If the sphere radiates at 20%, calculate the power radiated. All right. So here's our new example. Whereas before we had an object with a certain temperature and it's going to radiate, and we want to know what's its power. Now we have an object at a certain temperature, but we place it in an environment which is at a different temperature. So that's the difference in how these questions are posed. The former, all I tell you about is the object, and there's no word at all about the environment. In that case, you assume the environment's at 0 degrees. Okay, or 0 Kelvin, I should say. You're in outer space. If I tell you about the environment, then certainly it's important to use it. Well, here I tell you about it, so we have to use the major equation. Power radiated is sigma epsilon A T object to the 4th power minus T environment to the 4th power. Well, before I start plugging the numbers in, let me make sure everything in my problem is of the correct units. Well, first of all, I have a radius here, which is 30 centimeters. So I'm going to have to convert the radius to 0.3 meters. Next, I see the temperature of the object is given in Celsius. So the temperature of the object should be the Celsius temperature plus 273, which is 1073 Kelvin. Okay. The temperature of the environment, also Celsius, that's bad. So I have to convert him. Temperature of the environment is the 30 plus 273, which is 303 Kelvin. So there's all my conversions. Now that I've converted everything which had bad units, I can start plugging numbers in. So I say, okay, sigma 5.67 times 10 to the minus 8. Epsilon, how good does it radiate? 20%. So 0.2. Area, the surface area of the sphere. Well, I know it's 4 pi r squared. So it's 4 times pi times the radius, which is 0.3 squared. Finally, the temperature stuff. So I have times temperature of the object, which is 1073 raised to the fourth power, minus temperature of the environment, which is 303 to the fourth power. Okay. So before I do this work, it's important that you converted correctly, because if I didn't do conversions, all these numbers are going to be way off. And so obviously your answer is going to be wrong. So the first step before you even try to solve this stuff is to look at all the units, make sure you're in meters, you're in Kelvin, you're in seconds, all that kind of stuff. If not, then just convert everything up front. That way you could use that information appropriately later on. Are there any questions about how I've set this up so far? All right, well, this isn't so hard. I mean, this is just multiplying crap, but I mean, it's kind of messy. You have a lot of terms, a lot of powers, all sorts of stuff. So we have to take our time. So I'll do this in multiple steps, slower than I normally would, but you know, we're learning it, we're getting comfortable. So let me go ahead and leave everything at the beginning the same, and I'll just work out the temperatures. We have 5.67 times 10 to the minus 8 times 0.2 times 4 pi times 0.3 squared times, all right, 1073 to the fourth power, 1073 raised to the fourth power. That's 1.326 times 10 to the 12 minus 303 to the fourth power. That's 8.429 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9th power. Ooh, big numbers. All right, now I'm going to subtract those two numbers. So I have 1.325558 raised to the 12th minus 842,889,2481. I get, what's in the parentheses here is 1.3171 times 10 to the 12th. And then everything else, I just write in 5.67 times 10 to the minus 8 times 0.2 times 4 pi times 0.3 squared. And now I can multiply everything. Everything's just a bunch of numbers. So this number times 0.3 squared times 4 pi times 0.2 times 5.67 raised to the minus 8. And I get at the end of the day, 16,892.49 watts. All right. So that's pretty good. If you were to redo this problem without the environment's temperature, the number is probably going to be very similar. Okay. And the reason is because you have 1,000 degrees versus 300 degrees. The 1,000 degrees, when you raise it to the fourth power, is huge compared to the other guy. You can look, this is 10 to the 12th, this is only 10 to the 9th. That's 1,000 times less. So that 300-degree thing doesn't make that big of a difference in our answer. However, if the environmental temperature was closer to the object's temperature, maybe it was 800 or 900 degrees instead of 300, then there'd be a significant difference in my answer. Okay, so one of the things, just to tell you how physics works in general, and especially engineering, is when you're given problems, the true problem is usually so complicated you can't really solve it. Either there's too many things to worry about, too many unknown variables, or the math literally is impossible. It's an equation that cannot be solved, or other issues can arise. And so what a true physicist does is they'll look at all the things which could affect the problem, and they'll say, okay, which things are so small of an effect that they don't really matter to me. You know, if it's 16,892.49 watts or 16,893.49 watts, well, that's not a big difference. 1 watt when we're talking about 17,000 watts is not a big difference. So if having this extra temperature, this environmental temperature, only changes my answer by 1, then in reality, unless it actually mattered being extremely accurate, I just drop it off and forget about it. Why deal with it? It makes my math harder. It's not going to change my answer all that much, so I'll just ignore it. However, there are times where you can't drop some things. You know, the things are of similar size, so they'll affect each other quite enough. And so I would not drop those terms. And that's kind of the creativity or the artistic aspect of physics, is given a real world problem, can you figure out what things you can ignore and what things you have to keep to make the problem easy enough to solve, but the answer is accurate enough to matter. Okay. Now, of course, in this class, if I give you the environmental temperature, don't ignore it. You have to use it. I'm giving it to you so you use this equation. But just as a look ahead, when you get to graduate school and you're doing research and stuff like that, this is the kind of stuff you do. You ignore certain effects because those effects aren't going to matter that much. And if you didn't ignore them, it's going to increase the mathematical computation by a huge amount. It's kind of like if you go to a restaurant and you order an appetizer, and they have, okay, you can get, I don't know, 6 mozzarella cheese sticks for $10, or you could get 7 mozzarella cheese sticks for $45. Well, who the heck is going to pay that extra cash to get one extra thing? Just get the 6 for $10 and you're good. Same thing here. If adding in an extra term makes it more accurate, but that accuracy comes at the price of harder mathematics, then you have to balance. Is it a good deal? Is the extra accuracy I'm getting worth it? Or is my approximation good enough? Things like this. Anyway, this example is all there is to it. You have an object. The object can be a sphere, it can be a cube. It'll be at a certain temperature. You place the object in an environment which is at some other temperature. And then I can ask you questions. What's the power radiated? How long should you wait to get this much energy? How much energy will produce if you wait a year? Just like the previous examples, only now we have this extra term sitting here. And you see, to use it, it's not that big of a deal. It's just an extra term. You have to be a little bit more careful in the arithmetic, but in terms of the physics or the concepts, it's not a big deal. Are there questions about this particular example? All right. Good. Well, certainly practice, because I guarantee you when you get to a test, if you haven't practiced this stuff, even if you know the equations, you may mess up in forgetting to convert something, or actually plugging it into your calculator. If you haven't actually physically done that before, then you can make mistakes in how you input the stuff in. So you have to practice. That's why there's the practice problems on Canvas. Also, there's a homework problem. So, you know, practice it before the test time comes. It's not that complicated of a topic. The equation's not that difficult. We're not doing calculus or differential equations. You just have to be careful in how you actually physically solve this stuff out. Now, the plan is next week, Tuesday, we will have our exam review, because at this point, we're done with the material for thermodynamics. So Tuesday, we'll have an exam review. I'll go over all the material we've covered thus far in the semester. So you can see what would be on the test. And it'll give you one last opportunity before the test to ask me questions, to see something worked out, whatever, on particular topics. Then, of course, on Thursday of next week, we'll have our first test. And just to remind you, which I'll do again when it's exam review time, the way the test works, it'll be online. It'll be posted to Canvas Thursday morning. You download it, you work it out just like you work out the homework. And then by midnight that night, 11:59 p.m. that night, the submission deadline. So you could do it in the morning, you could do it during class time, whatever. We will not have class during that day because you're having your test. So you could take this class period to work the test, and then when you're done, submit it. You don't have to wait till the nighttime, but you have till nighttime in case other things are going on. Also, as I said, there's a homework problem that was posted about this material, radiation, and it's the last homework for this thermodynamics topic. And I think I have that due Tuesday of next week. Okay, so you'll be able to get it in before the exam on Thursday. But that's the plan. After that, we'll, of course, go on to the next topic of physics we'll discuss. I think it's probably going to be fluids, but I haven't decided for sure. Anyway, that's all I have for you today. We'll let you off early. If you have any questions, you're free to stay and ask me questions. If not, enjoy your weekend, and I'll see you next week.
Thank you. Have a good weekend.
All righty, you too.